Hi everybody, this is going to be the start of Chapter 6, and in Chapter 6 we're going to start working with quadrilaterals, so we're going to move from triangles, three-sided figures to four-sided figures. For our first section, 6.1, we're going to look at different types of polygons, so not just quadrilaterals, but all types of polygons. All right, so we've mentioned polygons before and talked about them, but we're going to go back and just define them again. In order for a figure to be a polygon, remember, has to be in a plane, a single plane, has to be formed by three or more line segments that are called sides. The sides have a common endpoint, or the sides that have a common endpoint are non-collinear, so they can't be in the same line. And each side intersects exactly two other sides, but only at their endpoints. So it can only intersect at two other sides only at their endpoints. All right, so just like in our triangles, which is a polygon as well, the endpoints of your polygon are called your vertices, or singular is a vertex. Below here are some examples. So we have our triangle, we have our pentagon here, and then we have a star, which is again a polygon because it's a closed figure made up of line segments. The way we name a polygon is you list the vertices in order. So here, when I talked about the triangle being in order, it wasn't too big of a deal because it will always end up being in order when you name it. But a polygon, other than a triangle, is gonna have, different. You have to make sure you go in order. So if you notice here, they started with D, so they have D, E, F, G, H. They went in order. Or you have polygon, like you can start at E, so it would be E, D, H, G, F. Doesn't matter the direction, counterclockwise, clockwise. It just matters that you stay in order. So I couldn't name it polygon like D, F, G, E, H, because that would not go in order. So if you start at H, then you go either clockwise or counterclockwise. So I could say polygon H, G, F, E, D, or, I could start at F and do F, E, D, H, G. But again, that order is important. All right, so here we are identifying if the figure is a polygon or not. If we look at A is made up of line segments, and they all meet at a point, and they only meet with, two line segments come together. And so like this line segment meets with this side and this side. So A is a polygon. B, we do have a line segment down here, but this is a semicircle. It is not a line segment, so therefore B is not a polygon. If we look at C, it's not a polygon. It's actually two polygons put together, because if we look at this vertice right here, notice there's three lines coming into it. That would not make it a polygon. So it's actually two polygons together. It would be a composite figure, but it is not a polygon. D, polygons have to be closed figures. We got this big gap here. The segments aren't connected, so that is not a polygon. And then E, it's made up of line segments. They only meet in corners or vertices, and not more than two vertices or segments come together at once. So E is a polygon. So A and E are our polygons. All right, we're just going to review names of polygons. Remember, a three-sided figure is a triangle. We've talked about those. Four-sided polygons are quadrilaterals. You can read the chart. Five-sided is a pentagon. Six-sided is a hexagon. Seven-sided is a heptagon. Eight-sided is an octagon. A nine-sided figure is a nonagon. A 10-sided figure is a decagon. And then a 12-sided figure is a dodecagon. There are names for like 20-sided figures and 30-sided. There's 20. I don't know if there's 30, but we're only going to go up to 12. And really, we're not going to do a lot with, the higher numbers. But if we have like a 13-sided figure, we're just going to call it a 13agon, a 14agon, or anything we don't know the name to. We'll just put the number here and attach the word gon to the end. All right, and then another way to classify polygons is if they are convex or concave. If a polygon is convex, then no line containing a side contains a point within the interior of the polygon. If a polygon is concave, it is not convex. And in the next slide, I'm going to show you some examples of concave and convex. So look at it. We were mainly in here, we are always going to deal with convex polygons and not necessarily look at concave polygons. Okay, so here the directions say if it's not a polygon, state why, but they're all polygons here. We're just identifying if it's convex or concave. So really, we're identifying is it a convex or concave polygon. And A is going to be a convex polygon because no line containing a side contains a point within the interior of the polygon. Okay, they're all on those vertices are all on the outside. B is the opposite. It is concave because if you look at this vertex right here or this one, the side is within the interior of the polygon. I think of concave, it like caves in. And that's kind of think of it as the inside of that polygon. So that is a concave polygon. And C, again, would be your convex. And again, A and C are the ones we're going to deal with in this course. We're not really, other than mentioning it today, looking at a lot of concave polygons. All right, we talked about equilateral and equiangular in triangles. Now we're going to look at equilateral polygons. And if you have an equilateral polygon, that means that all sides of the polygon are congruent. So this figure right here would be an example of an equilateral polygon because all the sides are the same. They're marked the same. An equiangular polygon can be found for the second figure, and the sides aren't necessarily the same, but all of the angle measures, if you notice, are all marked the same. And then a regular polygon is a polygon that is both equilateral and equiangular. So a regular polygon is going to have all sides and all angles the same. And get used to the word regular. If they say it's a regular pentagon or a regular quadrilateral, that means whenever you hear the word regular, all the sides are the same, all the angles are the same. All right, so here we have 3 polygons, and we want to determine if they are regular. And again, remember, regular means that all angles and all sides will be the same. So I look at A, all 5 of my sides, and again, sorry, I'm not a very great drawer here, are marked the same length, and all 5 angles are the same. So A is, yes, a regular polygon. Now B, if I look, all the sides are the same length. They're marked all with 1 tick mark, but they don't tell me anything about the angles. And again, this is where you don't really want to assume. And, it doesn't, looking at it, it doesn't appear that way. But again, we're not assuming. But if they're not marked, this is not a regular polygon because all the sides are not the same. And then for C, all 4 sides are the same. They all have 1 tick mark. And then if you look at angles, they have 2 different angle measures. So that means that this figure is not a regular polygon because all the angles and all the sides are not the same. All right, sometimes we'll talk about the diagonal in a polygon. And a diagonal is a segment that joins 2 non-consecutive vertices of a convex polygon. And again, we're only dealing with our convex polygons. So if we look here in a quadrilateral, from each vertice, there's always going to be just one diagonal. From a pentagon, from each vertice, and again, it has to go to a non-consecutive vertice, so it can't be attached, it can't share a ray for an angle. There are always going to be, from each vertice, two diagonals. From a hexagon, notice it keeps increasing. Now we have three diagonals. A heptagon, how many diagonals do you think it would have from one vertice? Hopefully you said 4, because that is correct. So we will talk about the diagonals in quadrilaterals and how they're related to the shape of the figure and the properties of those. All right, and the last theorem we're going to look at in this section before we do one more problem is the interior angle sum of a convex quadrilateral. So again, we're looking at convex quadrilaterals. Quadrilaterals have 4 sides, and all 4 angles in a quadrilateral always add up to 360 degrees. And I want you to think about the quadrilateral we just saw in the last picture, and we were drawing diagonals from one of the vertices. There's only one diagonal. Notice it makes 2 triangles. So the angles in this triangle add up to 180. Excuse me, and the angles in this triangle add up to 180. 180 plus 180 is going to give us our 360. So those diagonals can help us out a lot, telling us what the number of degrees the angles would add to in a polygon. All right, so here they just want us to find the value of x and then find the measures of angles C and D. So we just talked about it. I know that all 4 angles in a quadrilateral will always equal 360. So I'm going to add my 4 angles together. I'm going to add my 127 plus my 125 plus 2x plus 3 plus x and make it equal to 360. Let's combine like terms. So we'll do our x's first. 2x plus x will give me 3x. And then if I add 127, 125, and 3 together, it's going to give me a total of 255. And that's going to be equal to 360. And then I'll subtract 255 from both sides. So now I have 3x is equal to 105. And divide by 3. So x is going to be equal to 35. So that is the measure of angle D. It's 35. And then here, if I do 2 times 35 plus 3, 2 times 35 is 70. 70 plus 3 will give me angle C is 73 degrees. And that is it for 6-1.